Everybody, we're getting ready to do lesson 7.4 part 2 of pre-calculus math today. And for 7.4 part 2, you got 6 points here will go into your notebook, and then 52 points here will go on your classwork sheet, which you should have in front of you, students. You should have that ready to go with your name on it, your date, and period. Students, you should have that filled out by now. And then we're going to go right into a notebook slide here, part 2, Gaussian elimination with back substitution. So for Gaussian elimination with back substitution, in example 2 of section 7.3, that was the section before, you use Gaussian elimination with back substitution to solve a system of linear equations. The next example demonstrates the matrix version of Gaussian elimination. So we're going to go into the matrix version of Gaussian elimination. The basic difference between the two methods is that with matrices, you do not need to keep writing the variables. So we ditch the variables for matrices, so that's kind of handy. So let's go into an example here that shows how to do that. Comparing linear systems with matrix operations. So here's a linear system, and we have our variables here with our linear systems here. So we need to ditch that, and we go into this. So we'll go into an associated augmented matrix, which is this here, which we ditch everything. We ditch our variables over here. See how we do that, students? Instead of just x, we have 1, -1, 2, 2, instead of having our variables over here. So it streamlines the operation here. And then instead of having equal signs, we have these like supercolons here, is what you'd call those almost. So add the first equation to the second equation. So our first operation here would be to add our first here to our second. And then when we get that, well, let's see what happens here. When we do that, these go away here, so we end up with y plus 4z. When we add these here together, we have y plus 4z equals 7. When we add our first equation to the second up here, and we add our first to the second, and then add the first row to the second row, r1 plus r2. So now when we have this situation, when we go, this would be the way that we have it here with the matrix operations here. This would be the way that we would use the correct terminology. So we end up here 1, -2, and 3, and then 9 here. And then when we add row 1, which is row 1 and row 2 together, we get this. So here is the result here on this line here for adding row 1 plus row 2. And then row 3 is just, it remains the same. But now we have this situation here, 1, 4, and a 7 on our row 2. Okay, so moving through this situation here, add -2 times the first equation, -2 times this equation here, to the third equation. So what does that look like in matrix form? So add -2 times this to our third down here. The way that would look down here, the way that you would enumerate that, or the way that you would write that, be -2 row 1 plus row 3. So when we multiply -2 times row 1, add it to row 3, we end up with 0, -1, -1, and -1, because -2 times 1 be -2, -2 times this plus that, -2 and 2x, this would go away. And then positive 4y and negative 4y be -1. Then -6z and 5z would be -1. And then -2 would be -18, and 17 would be -1. So here's our new row 3 down here. So now our next step here, add the second equation to the third equation. So we're going to add our second here. We're going to add our second to our third. This will go away. And then 4 and -1 will be 3. And then 7 and -1 would be 6. So here is our new third row here. And we're still left with this here. So this is after our add second equation to third equation. And then again, the way that would look like here, and using a matrix here with the row kind of terminology here, be row 2 plus row 3. Row 2 plus row 3, we end up with this down here. Here's our new row 3 now. Okay, moving right along. Here's our original system here. Multiply the third equation by 1/3. So we multiply our third equation here by 1/3. Be 1/3 of 3 would be 1z, and then 1/3 of 6 would be 2. So this would be our new system here. And then the way that would look up here would be this 1/3 row 3 would just be 0, 0, 1, 2. That would be the way it would look here. Multiply third row by 1/3, or 1/3 row 3. So that would be that situation there. Now, at this point, you can use back substitution to find that the solution is. So we know our z here equals 2. Z equals 2. So z equals 2. We can put that up here, and we get y plus 8 equals 7, and move this over here. So get y equals -1. Now we can solve this up here. And then when we plug that in up here, we'll get x equals 1. So now we have our triplet, or ordered triple here. So as was done in example 2 of section 7.3. So that'll be the way of back substituting. Once you find one variable here, z, you can put that up here and solve for y. And then when you know y and z, you can put that up here and find x. Is kind of the Gaussian kind of method there. Okay, so let's try a guided practice in exercises 31, 32, and this one is 31. A, perform the row operations to solve the augmented matrix. B, write and solve the system of linear equations represented by the augmented matrix. And C, compare the two solution methods. Which do you prefer? So that's up to you. So let's get on one here. So our first task here is to add row 2, row 1, and then add -2 times row 1 to row 2, multiply row 2 by -1/4, and then multiply row 1 by 1/3. So we have a whole bunch of things here to do. And then once we do this, row 2 plus row 1, when we add row 2 and row 1, we end up with 3, 0, -6. So 3, 0, -6, yeah. Then we still have 6, -4, -28. And then the negative of 2 times row 1 plus row 2. So when we multiply row 1 now by -2, so we go back to our original here, we get to, well, actually we're going to multiply this here by -2. So it'll be -6 plus 6 would be 0. Then that would be 0. Then -6 times that would be +12. So that would be -16. So this will be our new second row here after we do this operation here. And then we do -1/4 of row 2. Then we end up with our 1 here and then 4. And -16 divided by -1, or rather multiplied by -1/4 would be 4. So here's our row 2 down here. And then 1/3 of row 1 would give us 1 and then -2. So that would be our operations that we've done that are designated over here. This is how they would be performed over here. And so our answer would be here. Here's our answers here. X would equal -2, and then y would equal 4. So that would be how we would come about that. And then here, I'm going to let you do this, students. I mean, I've done that first part. Now you step up and do this part, okay? And this is your answer sheet, 4 points here for you. This is your independent practice. And then C, which system do you think is easier? And you have a substitute method here. So say which is easier there between the two methods there of solving. Okay, moving on now into another notebook entry. The last matrix in example 4 is in row echelon form. The term echelon refers to the stair-step pattern formed by the non-zero elements of the matrix. To be in this form, a matrix must have the following properties. So row echelon form and reduced row echelon form. So we have two different kinds of echelon forms here. A matrix in row echelon form has the following properties. 1. Any rows consisting entirely of zeros occur at the bottom of the matrix. That would be a row echelon form. 2. For each row that does not consist entirely of zeros, the first non-zero entry is 1, called a leading 1. So the row echelon has all zeros. Any rows consisting entirely of zeros must occur at the bottom of the matrix. A matrix in row echelon form is in reduced row echelon form when every column that has a leading 1 has zeros in every position above and below it. So that would be a reduced row echelon. When you have just 1s and zeros, you're in a reduced row echelon form, and below is its leading 1. So it has what's called a leading 1. It is worth mentioning that the row echelon form of a matrix is not unique. That is, two different sequences of elementary row operations may yield different row echelon forms. The reduced row echelon form of a given matrix, however, is unique. So the reduced is unique. The row echelon is not unique. So when it's reduced, that narrows it down to a unique system there. So let's try one now. Row echelon form. Determine whether each matrix is in row echelon form. If it is, determine whether the matrix is in reduced row echelon form. So, okay. The matrices A, C, D, and F are in row echelon. So these are in row echelon here. They have 0, 0s, and 1s here. On our leading here are all 1s here. These are all leading here. They have leading 1s, so they're reduced row echelon here. So you have a leading 1 here, and then leading 1 here. And then this down here is zeros in the bottom here, zeros. It's not all zeros there. This is down here. This is down here. This is reduced. The rest of these are just row echelon. The matrices in D and F are in reduced. So these are reduced here because these are all zeros on your bottom row here. So these are unique here. These will provide a unique solution set for this system, is what it amounts to. Okay, so once we've got that out of the way, because every column that has a leading 1 has zeros in every position above and below its leading 1, above and below, above and below, above and below, above and below its leading 1, the matrix in B is not in row echelon form because the row of all zeros does not occur at the bottom of the matrix. So we don't have all zeros down here. is not in row echelon form because the row of all zeros does not occur. See, these are zeros over here, so the matrix in B is not in row echelon. This is not row echelon. This is zeros and ones here. See, E. The matrix in E is not in row echelon form because the first non-zero entry in row 2 is not a leading 1. So this here is not a leading 1 here. And then same thing here. Well, this not bottom row though. I mean, we don't have a bottom row here. B, the matrix in B is not in row echelon because the row of all zeros does not occur at the bottom of the matrix. So this is not in row echelon because this should be all zeros down here, and it's not. And then down here for E is not in row echelon form because the first non-zero entry in row 2 is not a leading 1. So that's the difference there. And they're fine designations, and it's good to know these, to know the terminology for row echelon and reduced row echelon. So this is the difference here. And if you need to go back through this video another time, that would be good to go back through it again. Okay, let's try one. Determine whether the matrix is in row echelon form. If it is, determine if it is also in reduced row echelon. So here is a matrix here for 35. If it is, so determine whether the matrix is in row echelon. Is this row echelon here? Well, let's see. So the matrix is in row echelon, is in reduced row echelon form here because we have zeros at the bottom row, and then we have leading ones here. But the important thing here is we have zeros on the bottom, so that makes these, and then you have leading ones here, so that would give it the designation of being in reduced row echelon. For that one, I'm going to let you do. So moving right along here, every matrix is row equivalent to a matrix in row echelon form. For instance, in example 5, you can change the matrix in part E to row echelon form by multiplying its second row by 1/2. What elementary row operation could you perform on the matrix in part B so that it would be in row echelon form? It would be the question. And the Gaussian elimination with back substitution works well for solving systems of linear equations by hand or with a computer. For this algorithm, the order in which the elementary row operations are performed is important. You should operate from left to right by column using elementary row operations to obtain zeros in all entries directly below the leading ones. So this is the idea behind the algorithm you use for row operations. So knowing that, let's try one. Example 6, Gaussian elimination with back substitution. Solve the system of equations. So we have this situation here, our system there. So write in augmented matrix. This will be the augmented matrix of this system here. Okay, we're going to interchange row 1 and row 2. So when we do that, this goes up here, and then this goes down here. So now we have a leading 1 here, which is handy. So we can solve probably everything below it from our fact that we have a leading 1. Okay, so continuing on our solving here. Here is our last step here on our matrix. So now we're going to go -2 times row 1. Here's our row 1. And then we're going to add that to row 3. So -2 times 1 would be -2. -2 times 2 would be -4. So we have 2 zeros there. -2 times -1 would be +2. That would give us our 3. And then negative 2 times 0 wouldn't change that, negative 3. And then negative 2 times 2 would be negative 4. And then negative 4 and negative 2 would be negative 6. So this is our new row 3 now. And then our row 4 would be negative r, negative row 1 plus row 4. So now we're just going to take the negative of this and add it down here to row 4. So negative 1 and 1 would be 0, negative 2 and negative 4 would be negative 6. Positive 1 and negative 7 would be negative 6. And then 0 and negative 1. And then negative 2 times 2 would be negative 4 and negative 19. Negative row 1. Oh, okay, so yeah, just be the negative of 2 here plus row 4 would make it negative 21. Okay, so we got this. We justified our row 4 here. Here's our row 3. So we have that. Now what are we going to do? We're going to go 6 times row 2. 6 times row 2 plus row 4. So 6 times row 2, this is what we have here. So 6 times row 2, which would be up here, plus row 4. So 6 times that, so this is where you get your 0 there. 6 times 1, negative 6 would be 0. Then 6 times 6, and then negative 6 would be 0 again. And then 6 times negative 12, and then negative 1 would be negative 13. And then 6 times negative 13 would be negative 18. And negative 21 would be negative 39. So now we're left with this. We need to fix that. So we need leading ones here, and we also need to fix that too. So far this is what we've got here. Perform operations on row 4. So second column has zeros below its leading 1. So okay, yeah, that already. So to do that, here's what we left with. So now we're going to take 1/3 of row 3. So we're going to get, this will become 1. And then this will become a negative 1. And then this will become negative 2 up here. And then we're going to take negative 1/13 of row 4. That will become a 1. And then this will become a 3. So now we have leading ones. Perform operations on row 3 and row 4. So third and fourth columns have leading ones. Now we have leading ones. Here's our leading ones. The matrix is now in row echelon form, and the corresponding system is here. Here's our corresponding system. X, Y, Z, and W. Using back substitution, you can determine that the solution is X is negative 1, Y is 2, Z is 1, and W is 3. Here's our W here. Okay, so let's go into our guided practice here. In these exercises, use matrices to solve the system of equations if possible. Use Gaussian elimination with back substitution. So here is our original system here. In matrix form, in augmented matrices, because we have our triple colons over here, this becomes 3, 2, negative 1, and 1. This becomes 1, negative 1, 4, and 2. And then this becomes negative 2, 1, 2, and negative 1. And then this is 1, 1, 1, 1, and then 6. So, the way to use Gaussian elimination with back substitution, we have 1, negative 1, 4, and 2. We're going to put this row up here and then put this row down here. We're going to flip rows here is what we initially do. So we have 1, negative 1, 4, and 2. Row 2 becomes row 1, 25. And then for this row here, we end up with a negative 75 here. So we're going to multiply negative 3 plus row 1. So negative 3 plus row 1. So we have negative 3 times this row here, and we're going to add it to row 1. And we end up with 0, 5, negative 13, negative 5, and then negative 75, because we're multiplying row 2 times negative 3. We end up with this, so we have a leading 1 here. And then now for 0, negative 1, negative 1, 10, 3, and 50, and 3 and 52. So 52 would be 2 times 25 plus 2. So we're going to multiply row 2, and we're going to add it to row 3. And then when we do this, this goes away, that goes away, or negative 2 goes away. Negative 2, see, positive 2, yeah, so negative 2 and 1, see, wait a minute here, see, 52 be 2 times 25 and 2, so it'd be 2 times negative 1 would be negative 2, and 1 would be negative 1, and then negative 2 times 4 would be negative 8, and let's see here, negative 8, oh, it'd be positive 2. 2 times, it'd be 2 times row 2 plus row 3. So 2 times row 2 plus row 3 will give us negative 1, 10, and then 3, and then 52. And then down here for row 4, we started with 1, 1, 1, 1, and 6, and we end up with negative 19. So you know we added 25, or rather a negative 25 to 6. So it'll be a negative row 2 plus row 4 to get our new row 4 here. So it'll be negative 2 times row 2 plus row 4 will give us our new row 4. So now we got zeros here below our leading 1 there. And we end up with this here. We need to get leading 1s across here is what we need to get. And to get that, I'm going to leave that up to you, students. I did the first part. So get your leading 1s here. This is your independent practice. I gave you a good start. And so continue that. And then here is your quadruplet down here, your ordered quadruple. It'd be down here. Okay, so this be 6 points for you to finish, hopefully in class time. It is classwork, so I expect you to finish this during class time. Now, going into page 15, notebook page, the following steps summarize the procedure used in example 6. Gaussian elimination with back substitution. So, 1. Write the augmented matrix of the system of linear equations. 2. Use elementary row operations to rewrite the augmented matrix in row echelon form. 3. Write the system of linear equations corresponding to the matrix in row echelon form and use back substitution to find your solution. Okay? Remember that it is possible for a system to have no solution. If in the elimination process you obtain a row with zeros except for the last entry, then you can conclude that the system is inconsistent. So let's do one now that exactly fills that. A system with no solution, solve the system of equation. We have this situation here. So putting this into augmented matrix here it is, your triple colon here. We just put our coefficients down here into this augmented matrix. And now we're going to perform our row operations. We're going to try to get a leading 1 here. So I'm going to take negative row 1 plus row 2. So I'm going to take the negative of this row and then add it to row 2. And then we end up with this here. And then we're going to take 2 times negative 2 times row 1 plus row 3. So we'll take negative 2 times this and add it to row 3, and then we get this. And then we'll take negative 3 times row 1 plus row 4. So negative 3 times row 1, we're going to add that to row 4, and then we get this. Okay, so our next step here in solving this matrix here, this is where we ended off with the previous slide. So we're going to add row 2 now to row 3. So adding row 2 to row 3 will give us our new row 3 up here. So 1, -1, -1, and 1, and then 2 and -4 to be -2. So here's our row 3 here. This is where we left off of there. Note that the third row of this matrix, this row up here, consists of zeros except for the last entry. This means that the original system of linear equations is inconsistent. So you can see why this is true by converting back to a system of linear equations. If you can just imagine this back in the original system of linear equations, I mean, how absurd would that be? It'd be very absurd. So because the third equation, 0 equals -2, 0 equals -2, is not possible, the system has no solution. So this system here has no solution to it. Okay, let's try one. Use matrices to solve the system of equations. If possible, use Gaussian elimination with back substitution. So here's our original system here. Here's our augmented matrix from this. And then doing 3 times row 1 plus row 2, 3 times row 1 plus row 2, 3 times row 1 plus row 2. So we go 3 times this and add it to row 2, and we're going to end up with 0, 7, and -62 here. And then 4 times row 1 plus row 3. So 4 times this added to that, and then we get 0, -4, and then -56. Okay, that looks good so far. So that's your guided practice. And let me go back here to your independent practice. Students, I want you to finish this on your own. And this is your answer sheet. This is 4 points here for back here. And that is your 7.4 part 2 of pre-calculus math classwork sheet. If you need another classwork sheet, you need homework sheets, solution PowerPoints, anything like that, here's my email. Contact me there. Thank you very much.